All right, yeah, so welcome back, everyone. I hope everyone had a happy new year. Um, Try to make this talk as interesting as possible. We're trying to get back into the swing of things. Basically, the crux of this talk is, hopefully by the end of it, anybody is able to take the code that they've written in a Jupyter notebook and deploy it on our HPC, our high performance computing environment here at CU Boulder. So without further ado, to the first slide. So the end of the line for notebooks, production. This might be sort of a provocative title for a slide. I'm sure many people have successfully used Jupyter Notebooks in production or run a Jupyter Notebook in order to get results for a paper, but oftentimes when you've developed code in a Jupyter Notebook that uses many resources, whether it runs for a long time or it needs to use a ton of cores or parallelization, you run into difficulties. If you write code that can no longer be run on your local computer, if you need to deploy it on AWS or you need to deploy it on the HPC, setting up your Jupyter server to deploy your Jupyter Notebooks can be anywhere from annoying to challenging to impossible. In the case of the HPC, if you run into permission errors. So, and of course, even once you go through all those things and maybe you set up your environment and get your code to run, if your code runs on the order of hours or days, I'm sure many people have experienced that your kernel dies or you lose connection to the server or any host of annoying things can happen when you run Jupyter Notebooks for a very long time. So these three things I don't really know much about. I never really troubleshoot them because I immediately just switched to the much easier option, which is to use a Python script instead, an executable Python script. So a Python script, an executable script specifically, is just a list of commands in a file written in Python that are meant to do a single job. Right? When you write an executable Python script, it differs from a Python module in that you aren't supposed to use the code in that script in other scripts. You're not supposed to import functions, import classes, anything like that in your executable scripts. And the advantage of these is that they're very lightweight and portable. All you need is a Python environment and your dependencies to run your Python scripts. You don't need to set up a Jupyter server. You don't need to deploy a Docker container, anything like that. And the Python script, the executable Python script, is a preferred way to run code on CU Boulder's HPC, right? On that shop. So just a little bit of background about the HPC. So there's 3 node clusters: Alpine, Blanca, and Summit. Each of these clusters have different types of hardware that run on them, and they're partitioned for different institutions to use. Alpine is a brand new node cluster that just came out last month. Summit is being deprecated currently, but you can still use it. We still use it, or at least I do, for many of the jobs that I still submit. It's available to all CU Boulder and CSU researchers and students. All you have to do is apply for an account. And there's many different resources that they don't just offer computing resources, but also have large file transfer and storage. So if you haven't looked into CU's research computing capabilities and the things that they offer, I would suggest that you check it out. There's a ton of different things. You will need some basic Linux skills most of the time to interface with the HPC, although they do offer interactive sessions, so you actually can spin up a Jupyter server on the HPC and run your Jupyter notebooks. However, the computing power is minimal on those servers. You might only get 1 core, and you might only get it for 12 hours max. So again, if it's something that you can't run locally and you need to use vast amounts of computing power, a script. Converting your Jupyter Notebook code into a script is going to be the way to go. The HPC is also free, so it's supported by CU, CSU, and the NSF. So as soon as you have an account, you can access massive amounts of computing power that would cost, hundreds, if sometimes thousands of dollars on AWS, supported by the university instead of by the project. So many advantages. So in order to show, again, what I wanted to accomplish today with this talk was actually teaching how to turn your Jupyter Notebooks into scripts and then deploying them on the HPC. And the only way I can think to do that is just to do a live coding demo and show everyone how we can take an example Jupyter Notebook and deploy it on the HPC. So in the attempt this, you guys can watch me make a bunch of typos and how it goes. It is rehearsed though. I'm not just doing this on the fly, so I practiced it a couple of times. So, and I'm going to say a bunch of stuff about coding that I'm going to say like it's a fact, but it's just my opinion. But feel free to adopt any tips. Okay, so first thing, what I've done is opened up my IDE, so my integrated development environment. This is called PyCharm. It's a JetBrains IDE. It's a super awesome IDE. If you're going to be coding in Python or developing in Python a lot and outside of Jupyter Notebooks, I would highly recommend using PyCharm, even over VS Code. And that's what I'm going to use today. So you can see in the file browser, I've created a new project. It's called an HPC demo. This is the directory which I'll be working in. I have the Jupyter Notebook that I'm going to be converting into an executable Python script. And then oftentimes when you want to run code for production, you have input files, right? Files and data that need to be read into the script in order to produce your results. So that's what I have here in this folder. We have two directories, planet data and training data, and then we have one TIFF file. So all three of these things will be read in at one point. Now, obviously the first thing to do is probably just to create our executable Python script to start. So we're going to make a new file, and we'll just call it the same thing that the Jupyter Notebook is called. Okay, and then I'm going to start with just a template of what most Python executable scripts look like. So at the beginning, you would have your imports, then you would have your functions, classes, and constants. Then you would have your main function. Then you would have your hook, or your entry point into the script. Okay. Now the hook is always going to be the same in Python, and that's with this logical statement: if name equals main. Then we'll define our main function. Let's write pass for now. Okay. So what if name equals main does? This will only evaluate true if you run this script as an executable. If you import any functions from this file, if name equals main will not be true. So any of this code will not execute. So if I were to make another Python file and say from veneer resnet DC planet import main, none of this code will be executed. Okay, so this is the standard for partitioning code in an executable script, right? This if statement here. Okay, so this is kind of our template. This is kind of how I think is the easiest way to start and to keep things organized. And now we have to actually start copying over our code from the Jupyter Notebook into the Python script. Okay, so I'm going to sometimes PyCharm has bugs. It's running on the new Apple chips, and sometimes doesn't like to do exactly what's told.
Was there one primary feature that sold you on PyCharm over something? So like
Yeah.
one pet feature that you just love so much?
It has everything. It has from being able to configure runtime environments to splitting the screen, which VS Code does too, but obviously it's breaking. I'm just trying to split the screen right now between two different files, and it's breaking, which isn't great. But, I can do without splitting it. So, okay, so this is our very first cell in our Jupyter Notebook. Okay, now we don't want to just blindly copy and paste code from each cell into the Jupyter Notebook. We want to actually look and see if there's anything that we need to change when we copy things over. This first cell is all imports and dependencies, so that's actually going to be fine. Let's just go ahead and copy and paste this entire section, and we're going to turn the linter off too because I'm not going to configure the environment here. Okay, so now we just have all of our imports. That's pretty straightforward. There's really nothing that we have to change there. Let's go to our next cell. Okay, so in the next cell, we're defining a class, right? So this isn't code that's necessarily going to be executed. It's code that's going to be used by our main function. So we have classes, we have a class, here's a method for the class here, and then we have another function definition. So all of this code will define globally in our executable script outside of the main function, right? These classes and these functions are going to be used by code in the main script. All right, so we'll put that in this section here. And we can look through the code, and we're seeing really nothing that needs to change.
Can I ask?
Yeah.
The content environment that they're pulling the imports from, or the library that they're pulling the imports from, how do I get that linked to the HPC in the first place? So do we get there?
Yeah. That'll be. Yeah, that's going to be a whole different section. So yeah, no problem. Yeah, that's good to anticipate. I mean, you see all these imports, and you're thinking, well, I mean, there's probably no way that an environment comes out of the box with all these things on the HPC. So we will have to configure our own environment for our scripts. So, okay, so we have all these classes, all these functions. And the next thing we want to do is, so our next, okay, here we're actually executing code. So when whoever wrote this Jupyter Notebook, they wanted this specific code to be executed to do something. And so this is going to go in our main function. But we see something interesting here. We see a file path, right? So what's happening is we're defining this file path variable. It's going back a directory and then DC and then training data. It's not very dynamic, this path. In fact, if we run this on the HPC, it's probably going to break unless we put all of this input data that we're reading in right here in the perfect spot in our working directory. As you can see, actually, if you're familiar with Linux, these two dots mean to go back a directory, and so this whole path depends on what our working directory is when we run this script, which is not good. So now we've hit I/O, right? We're reading in data, and potentially we're going to be writing out data. So how do we take care of that? We're writing a script. Well, what we need to do is actually define a place where all of our input data is going to be on the HPC, and where all of our output data is going to be written to on the HPC. We're going to use absolute paths to define these things. We're not going to use relative paths that depend on the current working directory that we're in. So this is pretty simple. We're just going to define, let's define first where we're going to store all this code on the HPC, what directory this is going to be in. So we're going to use os.path.join to concatenate all of our paths. You really should never use slashes in your code ever. You should always use path joiners. And because we're going to use an absolute path, this os.path.sep is the path separator character, but it's platform specific. So if you're running this on Windows, it's going to be backslash, unless it be a forward slash. Again, it's just way more dynamic than just writing dots and a bunch of slashes in your paths. Things can break. Okay, so in the HPC, there's a directory called projects. Every single person that has an account on the HPC has a projects directory. So it's next to the root. So it goes projects and then your identity key. And then you can create whatever directories you want in there. And there's gigabytes and gigabytes of storage available to you in the projects directory. Okay, so just to make this as dynamic as possible, we're going to use the user environment variable to define what the identity key will be on the HPC. And then we'll call this veneer, VNIR. So that's where our projects, all of our files and input data and output data are going to be stored. And then our data in is going to be projector, and then we'll just call it data in. And then data out will be os.path.join. Out. Now, we don't want to just put all of our output data into one output directory. Imagine you run this 10 different times and you get 10 different results. Or you run it one time and only gets halfway through and it breaks. If you keep trying to write output data to the same output directory, you're going to run into file collisions, and you're trying to write data to a file that already exists in that location, right? So every single time we run the script, we want to create a new output directory to store that runs output data. And the best way to do this is to use, so we have our data out directory. Now within data out, we're going to have new directories for each run. We're going to call them, they're going to be named after the Slurm job ID. Slurm stands for Simple Linux Utility Resource Manager, and it's what most HPCs use to manage jobs. So when a bunch of people are trying to submit jobs on an HPC, Slurm is the engine that makes sure that they're run in fair and efficient order. And so every time your jobs are run on the HPC, this Slurm job ID environment variable will be defined with a number, a unique number for that job run. So now we have, not only will this output data directory be unique, but you'll also be able to tell from which job this data belongs to. Right? Okay, so now we have our data in and our data out defined. Let's see how I'm doing on time. That's 11:35 or 11:40. Okay, so now we have all of our input data and output data locations defined. So now we can get rid of this path. So we look at our input files, and all that we have is training data. So training data, this directory here is actually going to go in the input data directory. That's where it's going to store, and that's where we're going to tell our code where it is. So it's going to look just like this. So now every time we have a path that we're reading in a file, we're just going to say, oh, it's about that join data in. Training data. Boom. Right, so now this looks a lot more robust and dynamic, I would say. This is There's no slashes, there's no double dots. We have one. Our path is defined at one point in our code. It's not defined at a bunch of different places. So, okay, that was the big first step. So now we have our input data directly defined, and every single time we see data getting read into the file from now on, we can use that data in variable, just like that. The rest of this code for here, there's no I/O here. We're just doing some things with some variables. Look at this next cell. No I/O, but what you do see is a couple print statements for logging. Okay, so this is another thing that's a little weird about the HPC, is that every time you submit a job to the HPC, it's going to create an output error log file and an output just standard output file, where all of your print statements are going to be recorded into this file, and it's going to be created automatically by Slurm. But what's weird is that you're going to have to add this flush equals true argument to each of your print statements. Technically, it only has to be added to the last print statement in your script, but as you're copying things over, you don't necessarily know which print statement's going to be the last, so I just put them in each print statement. And again, this is just going to flush the output to that file. Otherwise, you're not going to see it. Okay, so if you're logging things, if you're doing any time profiling with print statements, you need to add flush equals true to each one. Okay, so no I/O there. We can just keep copying and pasting this. Okay, now be careful here, right? You're going to be inside this for loop. It's very important that you make sure you unindent, get out of any for loops before you copy and paste the code. It's just little things you can run into when you're quickly copying and pasting code over. This is really just logging, but we'll copy it over here. Okay, so we have some more I/O here. We have some more just reading in files. Again, so if we look here, we have this file, this DC022:16. This is just going to go right into the input data directory. It's not going to be this double dot, this DC, all this stuff. So we'll define this path as data in. Right, same thing with this path. We have planet data right here. This is going to be in our input data directory. Just like that. So no more slashes, no more dots. In my opinion, you should never write paths in your code that depend on the working directory that you're in. You should always use absolute paths, and you should never change the working directory while your script is running. But it's just, okay. Another thing, this is interesting. If we're just blindly copying and pasting, normally you've written this code, so it's not, you would already know what your code is doing. But if you're ever doing this for someone else, don't like that. This block of code, there's some print statements, so I would add flushes to that. But what this code is doing right here is actually selecting whether or not we're going to use GPUs or we're going to use CPUs for the model training. Yeah.
I'm sorry. There are 3 questions on
Oh, yeah, sorry. Yeah,
first, could you share this example script after this session?
Yeah, of course.
Okay. Second, is there a reason not to use Python logging capability on the HPC?
You could, for sure. I mean, Slurm already kind of, yeah, if you already have logging built in to your code, then yeah, I would just use that instead. It's always better to use logging than use print statements, but it's just a little more complicated. But yeah, certainly logging will work for HPC.
Okay, and then the third one, I'm assuming that this file is on the local computer. Can PyCharm also open the remote file on the HPC?
Yeah, you can actually use PyCharm with the professional edition. It's like $299 a year, I think. But you can create an SSH connection to your servers and open up your files and all your code from PyCharm. But the free version doesn't have that, so I wouldn't be able to SSH on the HPC with this. Yep, so this block of code here is deciding whether or not we're going to use CPUs or GPUs. So to me, when I first saw this code, I thought, okay, well, this code stands to gain from using GPUs, right? So when I'm submitting my job to the HPC, you get to choose what resources you want to ask for. Do you want to ask for CPUs? You want to ask for GPUs? You want to ask for a ton of memory? You want to ask for a ton of cores? So immediately when I saw this code, I thought, okay, we should ask for GPUs. Some code would just be a complete waste, right? There's nothing that would stand to gain from using a GPU. But this code certainly will. So. Which we'll get into resource allocation when we get to the HPC. So, okay, yeah. So all this code is provisioning GPUs or CPUs. Okay. So this next block of code looks like we're training the model, actually, which makes sense due to the previous cell. So we'll copy all this, make sure there's nothing going on with some print statements. There's, I don't see reading in any files, it must have already been read in. Okay, so still no files being read in and nothing being written out. So go to the next cell. Okay, so this is interesting too, right? If you're running, the amazing thing about Jupyter Notebooks is that you can execute each cell and it's interactive. If you plot something, you can see it right there in your notebook. If we're going to be submitting jobs to run on Linux, it's just going to execute things. It's going to be behind the scenes on a different node that you really can't even see. So you're not going to be able to see the plot. If you run plt.plot, you won't be able to, it's not going to pop up on your Linux SSH connection or anything like that, right? So you have to actually, if somebody's plotting something, or if you're plotting something and looking at them in your Jupyter Notebooks, you need to save the plots and actually write them out when your script is running, right? So let's copy and paste these things. And I'll copy all this stuff. plt.show, we're not going to need that because we can't show it. So every time after plt.plot, plt.savefig, I'll stop path.join. And now we're going to use our output directory, right? We're going to write this to our output directory for this run. That's where we're going to have all of our plots saved. You can just call this losses, I guess, just taking a hint from what's the data variable that's being plotted. We'll do the same thing here. This would be epoch training losses. This is going to be epoch validation. And I think plt.savefig will just add a .png by default to all those file names. You could add a different extension if you wanted, but we save as PNGs. Okay, so we've read in data, we've written out data, we use our input data directory, we use our output data directory. And last thing here, so it looks like we're saving the models. We're we're outputting more data. And then we are saving some arrays to text files. Okay. So again, we're writing some stuff out. Let's make sure that all the paths are fine. We have the save res equals true, and then we just have if save res. Now, I normally just wouldn't touch someone else's code. If it works, it's fine, but this obviously can be unindented. This can be saveder, files planet. That's not going to work. That's just like a relative directory in whatever working directory you're going to be running this out of. So that's not going to be good. So let's make sure this will be in our output data directory, right? Data out, files planet. So the saveder variable, it's going to see if it exists. It's going to make it if not. And then it's going to save a bunch of stuff to it. And these file paths are fine because they use saveder, which is this absolute path here. And I make dynamic file names for it, which is great. One thing I forgot is that at the very beginning of your main function, you should make your output data directory. Make sure that's written. That should always be the first thing you do. So that way you don't get an error if it doesn't exist. Okay, so at this point, I would say this is good to be, first attempt to run on the HPC. You might run into some errors, but it might take a few tries, but they're not. You can submit a lot of jobs to the HPC that error out, and they don't get mad at you or anything like that. They're not going to email you and say you're. I think they like when people use the resources, I think, so just use them up, like ask for a lot of them, stuff like that. But, okay, back to your question earlier, Ty, our runtime environment. So we have all these imports. What's going to be the easiest way to provision that runtime environment? Right? We're going to actually create a conda environment on the HPC, and then we need to install all of these packages. The easiest way to do that is actually just going to be to create a new file called requirements.txt. Sure, Sue codes in Python a lot is familiar with this. And then all you have to do is, just like if you were to say pip install, like pip install, let's say like geopandas, for instance. All you have to write is the name of the package in this file. So you write geopandas, company. You can do versions 1.0.61. And so this is where you're going to see, you're basically just making a list of all of the packages that pip needs to install. And you can say, just give me the newest version. You can just put the name, or you can specify the exact version that you want with the double equal sign. I'm not going to write out this whole requirements.txt file just for the sake of time. I already have all of this stuff on the HPC. So I'm going to connect to the HPC. Now, you may be wondering, okay, I have all this code on my local machine. I have all these scripts. How do I actually transfer them to the HPC, right? And I will show you that in just a second. Show my password.
You're broadcasting this to us.
Yeah, I'll try to do it super fast, like within a frame.
Everybody close your eyes.
Yeah, I covered that up. Okay, I'll change them all after. Okay, so you got to put in your password, then they're going to send you a push notification for the two-factor authentication. Okay, so you prove that now you're in. And let's just get a lay of the land really quick. So if we look at where we are, I'm immediately in home, and then my identity.
Sorry, there's one more question on mine. If we have created an environment, if we have an environment created using a YAML file, can we just call that environment through conda at the head of the script?
Yeah, totally, yeah. If you have certain ways that you like to create in your environments, by all means, that also. Okay, so we're in home. So home doesn't have much storage. Home is just kind of where to put like scratch files and things like that. It's projects actually that has a lot of storage for your projects, right? So your output data, your input data, things like that. So it's always gonna be projects, then your identity, and then we call this veneer and VNIR. And you can see I already have all this stuff on here just for the sake of time. So we have our data in folder, we have our data out folder, we have our logs, where each runs output and error logs will be stored. We have our requirements.txt file, which we'll take a look at that really quick. This is what it looks like. So it's GeoPandas, matplotlib, numpypandas, torch, all that stuff. We have, of course, our executable Python file, right? Our .py file, not our .ipynb notebook. But this is the executable file that I just wrote, right? Again, if you want to transfer all these things, I really should show that really quick. So how you would do that is you would open up a new terminal. You would go to wherever your code is. So I can see all these files right here, and I would use the SCP package. It stands for secure copy. It's like secure shell is SSH, SCP is secure copy. So you would do SCP, the name of the local file that you want to transfer, your username and the server host name, which is your identity at, and this is the host name for CU HPC is login.rc.colorado.edu. Put a colon, and then you would put your path. So if we look at the other terminal window, the path that we're at right here is projects, your identity key, right? So that's what you would do. And then if I were to press enter right now, it's gonna ask for your password, and it's gonna ask you to authenticate on Duo, and then it'll transfer the file. You can also transfer entire directories this way. You just need to add the R flag for recursive at the beginning of the command. I don't want to go into that too much because we're running out of time, but SCP, that's how you transfer things between local computer. There's other ways to do it, but SCP is the easiest. Okay, so all these files are on here. That's great. So now we actually want to create our runtime environment, right? So we need to, and there's many different things kind of that you have to understand before you do this, but there's different types of nodes on the HPC. So there's different computer hardware partitioned for different things. So there's hardware that's reserved just to provision logging in to the HPC. It's called a login node. And then there's a whole other set of hardware just for installing software called the compile node. And then you have all of your actual compute nodes after that, right? So you are supposed to, there's very little computing power reserved for the compute nodes. It's a little bit more for the compile nodes. So if you're going to provision your environments and install software, you need to be on a compile node. And the way to do that is you do SSH scompile, and that's going to connect you to a compile node. And it's actually going to change what directory you're in. So let's go back here. Okay, now there's a bunch of different modules. So there's a bunch of different software installed on the HPC, but you don't have it immediately available to you. So if you want to access Anaconda, you actually have to load Anaconda module into your session. So you would do module load Anaconda. These are all things that the people at CU Research Computing have already decided to install on the HPC. This isn't, oftentimes you would need pseudo privileges to install different software. So you kind of just have what you're given. I do have Anaconda, so immediately I'm in my base environment. So you'd want to create a new environment, right? Anaconda. So I always forget this command. Any help from the chat?
Yeah.
Yeah.
There,
Oh, this one here. You can have this condo create. Oh, there we go. Guess okay, so we just do conda create. We're going to call this HP. Okay, so now it's going to provision that for us, and then we can activate it. And then now that we have our requirements.txt file and we've in our activated environment, we used to pip install R for recursive requirements.txt. Okay, then you just press enter. And just for the sake of time, there's no reason we need to sit here and see a bunch of packages download. So, but that's the command that you would run. Okay, so now we would, after everything gets installed, and you'd have your environment provisioned. Now it's time to actually submit a job to the HPC and have your code run. So the way to do that is again through Slurm, which I mentioned earlier. And Slurm works by submitting bash files to it with Linux commands and then special Slurm directives. So if we look, this sbatch_veneer.txt file is the file that I use to submit jobs for this project to Slurm. Okay, so it's just a text file. You could just do touch. You could just do vim sbatch_veneer.txt to edit it. This one's already filled out. There's many different templates online for Slurm files, Slurm batch files. I end up just using the same one, usually from different projects, and I just change what needs to be changed. So really quick, I just want to go through, first you need to say how to interpret this file, which is to interpret it with bash. Again, there's templates online for this. And then you need to actually input all of your Slurm directives, right? So this is where we ask for specific hardware and specific runtimes from the HPC, right? So nodes just means it's like a cluster of cores, and most jobs are just going to use one node. I can't even think of a use case off the top of my head for multiple nodes, because tasks is going to end tasks here will provision cores, compute cores for you, CPUs, GPUs, the number of cores that you want. So as we saw earlier, this code uses parallelization to train the model. So we can stand to gain from using many cores. So I've asked for many cores. Again, if your code doesn't stand to gain anything from using a lot of memory, using GPUs, using a lot of cores, then don't ask for them. But if it does, ask for as many as you can. So the next thing is the time that you want your code to run for. These jobs will time out. Usually this will default at like 4 or 12 hours or something like that, unless you ask for more. This code turns out to actually take a very long time to run. So we'd ask for 168 hours. I think you can ask for up to 7 days usually for a job. And then if you really need more time, you can usually email the research computing people. The partition, so again, all the hardware that's on the HPC is partitioned into different sections. You have your high memory cores, you have your GPUs, you have your general purpose CPUs. Because this code also uses a ton of memory, uses 500 gigabytes of RAM to run when it's training that model, we need to use the SMEM, the Summit Memory Partition, which uses all the high memory nodes. We're going to ask for 500 gigabytes. These output and error directives, this is the output, this is all your logging, where all of your logging will be written, or at least your print statements. So this is going to be written to logs, that logs directory, and then this is going to be the job ID, this %A. So each output file and error file, which if your code errors out, this is going to have the stack there. Will be named after the job, right? Their name will be the job ID. This %A is the job ID. The job name, just call it whatever you want. This one, call it something specific. This is year 2022. You can also have it email you when the job starts, the job finishes. You know, you submit a job and it might take a couple hours until it gets through Slurm to actually run. So the email will tell you when it started. It will also tell you if it ended or if it failed. These next three directives here, module purge, module load intel, module load anaconda. So again, there are things installed in the HPC, but they're not immediately available to you. You have to load them. This module purge and module load intel should basically be in every script. This comes straight from the CURC documentation. You want to get rid of any modules that you already have loaded in, and you want to load intel. You want to obviously load anaconda because we're going to be using a conda environment when we run the code. And now the next thing, and as you can see, all of these commands are just Linux commands. So these three things here, you could just type into the command line and they would do something. And so of course, this is being interpreted as a batch file. And so now the next lines you just write as if you were typing them into your command line and running these things sequentially. What would you do? You would activate your conda environment first, right? So you would write conda activate veneer. I call it veneer demo. Just to make a new environment. But you'd activate your conda environment, and then the next thing you would do is simply call your Python interpreter, which since your conda environment is activated, you can just type Python. And then the next argument is just a path to your executable, right? We have it in projects, identikey, which you can use the user environment variable, veneer ResNet, DC planet. So, yeah. Now, in order to actually submit that file, so it's all filled out, it has everything typed correctly, you're going to write sbatch. This is the Slurm command for submitting a batch job, and then the name or the path to that text file that you just wrote. So now it's going to say submit a batch job. And then if you want to look at the status of all the jobs that you submitted, you can use this SQ with the U flag and then your identikey, and it's going to show you all the things. So I saw this, I was rehearsing for this, but the Summit cluster is currently down for maintenance. So as you can see right here, it's saying that this is the job that we submitted. This was the name. This is a partition, and we're requesting one node, but the node is not available. It's reserved for maintenance. Now, if the node was up, it's either going to start running immediately if nobody's in front of you and asking for those resources, or it's going to give you an estimated time when your job's going to be submitted. Now, sometimes if you ask for a ton of resources, so earlier I said to ask for a ton of resources, you can't. I would start like that, and then if they say that it's going to take 2 or 3 days to actually get your job to run, okay, then maybe dial back a little bit until you get a reasonable time that your job will start. Then we'll run. You're going to have your output data. It's going to write all of your files there. It should create new directories for each run with the job ID. If you go to logs, you're going to see all your different logs for each run. And you can just like look at an example file. Yeah. So I added some time profiling, and this is all the print statements telling us our training accuracies and all these things. Print off that job. So, okay, yeah, I think 2 minutes over. So, thanks. Hopefully, you at least have an idea of how to do all of this. It's not super hard, but there's a lot of things that you have to remember. Of course, feel free to email me or send me a message on Slack, whatever, to remind you of different steps you need to take or just help you out. I'm more than happy to.
That question in the chat about a YAML file.
Yes.
So, often the notebooks will use a YAML file to format the whole notebook. How would you transfer those settings over to the HPC, I guess? I don't know.
Yeah, I've used YAML files to set up environments, but not too much for Jupyter Notebooks.
My other question was about doing your for loops in Slurm versus in Python. Like when do you ever recommend sort of pulling your for loops out or doing multiple batch scripts or sort of managing your batching in Slurm rather than in your Python script?
Yeah, so if, let's say you're running a script with a bunch of different inputs, but you're saying like you would, in your code, you would have all your inputs in a list and then you would do a for loop to do those inputs.
Yeah.
So
maybe like running through space, like you're doing a scheme through space or something like that.
Yeah, exactly. If I would say if they're going to be running, if each input is going to be processed quickly, I would read them in a for loop in a single job. But for instance, like when we did the SDM stuff, there was a new, each input it could take up to a day to run each input. And so the best thing to do then is to actually have a file, like a CSV file, with all of your input parameters. In this case, it was a file path. And then you can use a job array. So let me actually go to the project. Okay, so if you look at, so you can actually provision an array with Slurm, with numbers, right? So you have, let's say your array, you could do something that was 1 through 100. There's a list of integers 1 through 100 in your Slurm file. And it's going to submit 100 different jobs automatically for you. But each of those jobs is going to have a different input parameter. 1, 2, 3, 4, 5, 6. And you can use each of those input parameters in your file that you're running to index that CSV file. Right, so the first job gets run with the input parameter 1, the first list, and that's going to take the first row of your CSV file as an input. The next job will run with 2, that's going to take the second row of your CSV file as input, 3, 4, 5, and so on. So yes, when each parameter takes a long time to run, I would absolutely submit them as separate Slurm jobs. If they're quick, if you can process a whole list of inputs in an hour or even a day, I would maybe put them all and submit it as one job.
That's how I crashed the wash user. I requested 1 million Thinking like it was not a big deal, but the Slurm queue list could not handle my million requests. It just like fried the whole thing and killed the home node.
Did they track you down and send you an email or?
Oh yeah. They found me real quick.
Yeah, I think when I first was submitting jobs, I was like, oh, they're gonna, there's a bunch of errors the first time. I was like, oh, they're gonna like find me out, they're gonna get mad, like stop submitting jobs and messing up. Don't worry about that.
Yeah. We found that it was like 3,000 to 5,000 you could do and not crash the thing, and the Slurm server could handle it.
Eric, there's one more question online. Is there a Slack channel for Alpine users that folks can join?
They keep sending emails, CURC does, about Alpine, but I haven't heard anything about a Slack channel. I would email rc-help@colorado.edu and ask them about that. They're super helpful. It's gonna keep going. But yeah, if you have any questions about the HPC, the people at RC help are super helpful. They have office hours every week, I think, that you can go to and just ask them questions about it. So I know the high memory node, high memory cluster for Alpine is currently down. Right now. They're still waiting on some hardware. So if you need to use high memory nodes, you need to use Summit instead.
Any other questions from anyone, online or in person?
That was awesome. Thanks.
Awesome. Yeah.
Thanks, Eric.
Yeah, of course. Thanks, everyone.